You have fallen into Event Horizon with Jonh Michael Godier. In today's episode, Jonh is joined by Dr. James Benford. Dr. Benford studied physics at the University of Oklahoma and in 1969 received a PhD in physics from the University of California at San Diego. He then worked at Physics International. In 1983, he investigated the use of pulsed power technology for high-power microwave generation. Dr. Benford developed a variety of microwave sources at very high power levels, built the largest high-power microwave experimental facility in the US, and developed a research group working in the areas of microwave source physics, microwave beam propagation, and microwave effects on electronics. His current interests include phase control of high-power arrays by phase locking of oscillators. His past experience includes work on electromagnetic launchers, pulsed power design, system studies, and the use of electron beams for many applications.
Dr. James Benford, welcome back to the program.
I'm glad to be here.
Now, you've authored some papers recently since we last talked, which I think was earlier this year, and there's some interesting things here. A new take on the Drake equation in regards to alien artifacts or searching for alien artifacts, and some other things. One thing you did in one of the papers was try to come up with an estimate on, or at least how we would come up with an estimate on just how many probes could be present on a place like the moon, long term, originating in star systems that just happen to pass by. Now, how often does a star system pass by our system close enough to place such a probe in it?
Depends upon the range of the probe, of course, but one way to look at it is if you want something that comes within 10 light years, there's a new star coming within 10 light years every 5,000 years. Within 1 light year, it's once every 500,000 year. In fact, the most recent case of that is Solstice star, which came very close. That is 0.8 of a light year, only 70,000 years ago.
Now, a lot of these stars are going to be, I believe, like Solstice star. They're going to be things like red dwarfs, predominantly, right? How often do we see something like a sun-like star passing by?
It's about an order of magnitude smaller than that, those numbers I quoted.
Now, with this, you conquer the sort of problem of distance, traversing enormous amounts of space. You don't really have to do that if your star just happens to be passing by an interesting star system, which presumably our system is and would be of interest to an alien civilization because of this one certain planet that has had absolutely weird oxygen levels for billions of years since the Great Oxygenation Event. So, assuming an alien civilization would be interested in a planet like that, this would be of great interest, wouldn't you think, to put a probe like that in?
Well, certainly. I mean, think of it ourselves. Suppose we were to find an oxygen atmosphere in an exoplanet that was, say, 7 light years away. We would make a big effort to observe it carefully with large telescopes and ultimately send a flyby probe, because we always do flybys first, and then to send an orbiter and then to send a lander. Even though it's 7 light years away, we could manage to do that sometime perhaps in the latter part of this century because technologies are improving steadily.
So this is something that we're getting close to, this idea of self-replicating probes that if 5,000 years from now a star system passes by us, we could look towards maybe stationing our own probe there, right?
We could station it there. It doesn't have to be self-replicating or semi-immortal. After all, there is a program right now that I'm working on called Starshot, which the intent is to send flyby probes to nearby stars. Now, very low mass at very high speed so that you could get, for example, at 0.2 of the speed of light, you can get to Alpha Centauri in about 20 years. So you can fly by Alpha Centauri, and you can send another probe the following week and the week after that. And you can send a fleet of probes to gradually take data about the star system. If Starshot goes forward, as it is right now at about $10 million a year, we will be able to do that by mid-century.
Say we do that. Now, with Starshot, that's basically just passing through a star system, right?
Flyby.
A flyby. Now, what would we have to do to actually station it there? Say we wanted to look at Proxima b long term. What would be different?
Well, you'd use you'd probably use rockets, nuclear rockets, fusion rocket probably. That's the most developed concept. Starshot is a photon beam propelled craft of very low mass, and the beamer stays on Earth, and the probe flies by. We don't have a beamer at the target star, so there's nothing to slow it down. So if you want to decelerate into that star system and to perhaps go into orbit around a planet, you need a rocket that's going to have a much higher mass. In fact, would be comparable to the largest ocean-going vehicles we have now, and would be a titanic effort to build, but we have these concepts for how to do it.
With Starshot, and this gets into another one of the papers that you've recently authored, with Starshot, we're going to have leakage around that light sail when we send it, and that leakage in principle should be detectable from a distance. Will any civilization out there be able to see, say within 10 to 100 light years, will they be able to see Starshot?
Far further than that. Actually, Starshot's beam of between 10 and 100 gigawatts is so powerful and so narrow that it would be visible across the galaxy as a leakage radiation around the edge of the sail, because the sailcraft, of course, the beam is always somewhat larger than the sail. So it's a highly visible leakage radiation that could be seen across the galaxy. And that's just a low power, that's just entry-level interstellar probes. If we were to have heavier ones, you'd have even higher power beamers, presumably laser beams, and that would be even more visible.
Now, is there any area of the spectrum, say you're beaming a power beam at a sail, is there any particular area of the spectrum that would be advantageous for it? And if that's the case, where should we be looking for evidence of leakage?
Well, in my view, it comes down to a cost argument, and we don't know anything about the cost of alien civilizations, but in our own, it turns out to be expensive to do, of course, in any frequency band you want to use. But right now, there are three credible bands. One is microwave, which we use for everything from cell phones to radars. And then there's millimeter wave, which we use generally for heating fusion reactors, but there's much higher frequency. And then there's lasers in roughly the optical. The problem is that the cost of a given watt of power goes in roughly the order I gave it to you. Microwaves are cheaper than millimeter waves, which are cheaper than lasers. Now, lasers may come down in cost with time, and I've been waiting for that to happen for a long time. And if we were to replicate them for some commercial process, such as, for example, LiDAR on self-driving cars, we might be able to get lasers to be very cheap. And until we do, the other frequencies will be cheaper to build. And so it really depends upon economics. The ultimate question you ask is, if I want a given mass to get up to interstellar velocities, what's the cheapest way to do it? And for choosing the frequency falls out of that asking that question. You don't choose a frequency and then just find out what it costs. You fix your costs and then find out what frequency can fix it.
Now, what of certain favorite frequencies? For example, 1420 megahertz, the hydrogen line, where SETI looks for, intentional signals. Would you even use such a frequency, though, could leakage be detected at that frequency from a light sail?
Oh yes. The microwave frequencies propagate across interstellar space with very little attenuation. And that's why people have always conducted SETI in the microwave bands, because it's the place where the interstellar attenuation is the least. Now, no particular frequency is required for power beaming. As long as it can just get outside the atmosphere, which microwaves easily do, then it doesn't matter if it's a gigahertz or 5 gigahertz or whatever. But that is important perhaps for radio astronomers to try to think of a magic frequency to listen to. But operationally, for a beamer, the selection of frequency is not important.
One question that comes to mind also regarding that is that we did once get a signal that was very strong at 1420 megahertz, and we only saw it once. The WOW signal of 1977. Could that have conceivably been leakage from a light sail?
It certainly could be. In fact, I've recently worked on that, and I'm now writing it up. And you ask, well, given the power that we received at that frequency, what kind of a leakage would it be? Would it be leakage from launching interstellar probes? Probably it could be, but probably it's much more in tune with the applications, the other applications of power beaming, that it's probably more like launching an interplanetary probe. And from that, if you say, well, you need a certain amount of power to launch an interplanetary probe, say from Earth to Mars, how would that be seen? Over what range would that be received at the intensity of the WOW signal? You get an answer like 1,000 light years. So power beaming from Starshot would be visible at that intensity at over galactic distances. It depends upon the application. The range at which that beamer would be located depends upon the application. So for the WOW signal, I think the most credible application is in the microwave. Since the WOW signal is in the microwave, it's probably power beaming to launch a probe toward interplanetary missions, or even lower energy missions such as launching a spacecraft into Earth orbit or into the orbit around a planet. That takes less energy and is most easily done in the microwave because of there's no absorption in the atmosphere the way there is lasers.
I seem to remember that there were two calculations done on the WOW signal, one by John Krauss and the other by Jerry Ehman. And if you take John Krauss's calculation, the WOW signal seemed to have what appeared to be a blue shift, very slight, and that it, or at least it could have been a blue shift. It also could have simply been the frequency that it was being broadcast at, which was just above the hydrogen line. But that corresponded with, as I remember, I think it was 10 kilometers per second moving towards us, which happened to actually match the background of the hydrogen clouds in the area where the WOW signal was detected, according to Bob Gray's book, The Elusive WOW. Would that speed, which is slow, I mean, that's slower than some of our probes, Voyager, would that 10 kilometers per second blue shift, would that be consistent with the light sail?
No. The light sail would be going much faster. Well, 10 kilometers a second is 1/3 of the speed of the Earth going around the sun. And we launch probes to Mars at 10 kilometers a second. It's just that it takes about a year to get there. And so one could do that with power beaming. And so that does fit. That is a low velocity for probes. But unfortunately, we have only so far just chemical rockets, and 10 kilometers a second and speeds of that order is all we can really achieve once you get outside the Earth's gravitational well. The Voyagers that you mentioned are going 10 or 20 kilometers per second at this moment.
With this idea of accelerating a light sail, you could get that up to relativistic speeds, or at least to some fraction of relativistic speeds, and go very, very fast, which would require quite a bit of energy. So if that's being done in the galaxy, it seems like it would be straightforward to detect, right?
Oh, it would be very detectable across enormous ranges, yes. However, it may not be easy to observe it again because, after all, it's not targeted at us. It's just leakage radiation. And such beams, for example, if it were targeted toward a star, you would point the spacecraft, drive it with the beamer ahead of the star. Just as you do in skeet shooting, you shoot ahead of the object you want to hit. So if we just happened to be where they had pointed it to be ahead of that star, we couldn't expect them to do it again later because the star would be in a different location.
Thus, it would be another wow signal since it couldn't be verified, right?
Another thing we couldn't verify because it wouldn't repeat, yes. But that is the problem, that leakage radiation may not be reproducible at all.
Now, if a civilization had some very stable leakage, that's going to point in a direction for a long time, and they happen to know that there's some sort of a interesting planetary system behind that might pick up that leakage, could they piggyback a signal onto their own leakage?
Oh, yes. In fact, I think that if we, when we get to launching spacecraft with beams, I have advocated that we put a message on that beam, modulated in some way so that they can understand some information from it. I've talked to some of my friends in the interstellar messaging community, that is people, technical people, and they say, well, sure, you could put some sort of a message on the beam, for example, by modulating the frequency slightly, because the acceleration of the probe doesn't depend much on frequency. So you could modulate the frequency and provide information without affecting the acceleration of the probe at all.
What if you were going to do that? What sort of message would you send? I mean, how would you send something that would be understandable to an alien scientist picking it up?
Well, I think that's a subject that's very widely discussed. I've always liked Frank Drake's idea that you'd send a picture, and basically it would be a number of pixels, so to speak, and that the number of pixels would be the product of two prime numbers, so that therefore it would be recognized that here's a very large number of pixels, but it happens to be a product of two primes, and therefore it could be a two-dimensional image, the number of pixels on one axis being one of the primes and the other axis being the second prime, and they would quickly interpret that as a picture. And that idea was advocated, 50 years ago, and they actually sent an image, Drake sent an image to a nearby galaxy, a primitive image, with a radio telescope. So I've always liked the idea of images, and I think it's very hard to think of how you would do anything except an image, since we have no common language.
Right, other than maybe something scientific, which has led to depictions of things like neutral hydrogen, because everybody should know about that, at least if they have science.
Yeah, and then at the other end they'd say, why did they spend all this effort to tell us about something we already know?
That might even insult them. Now, this changes, though. This seems to me that this would change if you have an artifact in the solar system. So if you have a dead probe that collected data at some point in the past and perhaps still had it, say, images of ancient Earth from millions of years ago, that sort of data would be unbelievably valuable to science. So you'd want to get it out of that probe. Do you think there's any way you could ever decode alien data from such a dead probe, providing it's still in good enough condition to actually preserve it?
Well, I can certainly think of a way. Just take the way I just specified. That is, code your images in the following prime number of pixels that I just recounted. Do that so that if it's ever discovered by people from Earth, they might be able to figure that out from looking at the data store, whatever that is, probably something like a hard drive or some other technology. Of course, they may have a technology that's so advanced we can't understand it. After all, if the ancient Romans were to see a hard drive, what would they think of it, and how would they get data off of it? Well, the short answer is that they wouldn't, because they have no idea what that technology is. And we might well find that it's unintelligible to us. But the big thing about a probe is that it's the ultimate technosignature. That's the word we use these days to describe some sign of a civilization, a technosignature, rather than SETI. It's the ultimate technosignature because it would contain all sorts of technological information about that civilization, just in the way they built the probe and what the technologies were.
Looking for these things within the solar system, you focus on three areas: the moon, Trojans, and quasi-orbital objects, to take a look and see if we, maybe someone left something there. Now, with the moon, which is a very large object, we also have a humongous data set from the Lunar Reconnaissance Orbiter, images of the lunar surface to very great detail. You can see Apollo landing sites and evidence of humans visiting there. But most of these images have not been seen by human eyes. So if there is something there, and if it is visible from a distance above the moon, how do we go about looking for that?
Well, I think the way to do it is not to get a marching army of people who would apply their own subjective judgments, so you could never be sure they didn't actually miss something. The idea that people are looking at right now, and there are three groups working on this at the moment, is to develop an artificial intelligence that would do the first order of sorting out those millions of images and try to identify some signs of artificiality in them. And you could train the AI by giving it pictures of course, all the objects we already know are on the moon, and then ask it to look at, say, images from Earth orbit of ruins on Earth, and then challenge it to find some objects on the moon where we're not quite sure where they are. For example, when the Apollo astronauts launched off the moon, they left behind when they mated with the command module, they left the booster behind. And it was in lunar orbit for a while, and then eventually, because of gravitational mass anomalies, crashed into the moon. We're not sure where they are. We haven't really gone to look for them as far as I know. We could ask this AI to try to find them. We could give it an orbital path and say, look along this path, see if you can find a lander. The ruins, that is, the wreckage of a lander.
One question about that, you can see clearly in some of these images, you can see the lunar rover tracks. Now, would that be something that such an AI could pick up? Say, whatever they were doing, they were mining on the moon or something like that, getting a little bit of raw materials and moving on, and left some sort of geologic anomaly like a road cut or a mine. Could we find that?
Well, certainly the human eye would notice it right away. There are, in fact, some photographs of things on the moon people do not understand. And the easiest thing, the thing that leads the eye to it, is generally a straight line or a continuous curved line. We are always looking, we human beings always look for patterns. And if you look for things like straight lines, it's easy for the human eye to see it. And I think it'd probably be easy for an AI to see it too.
Now, once we found something like this, and we find something strange on the moon, we'll call it the monolith, in a nod towards Arthur Clarke. So, say we see something like that, what do we do? As far as investigating it, that would seem to me to be something where you would drop everything and go investigate it. But how prudent would that be? Is there any chance that the thing could still be active even though it's been there for millions of years? Can it have some sort of self-repair ability or self-replication ability that could keep it going that long, or is it very much more likely that it's just dead?
It's much more likely to be dead because our artificial objects have certain lifetime, or at least those that are active objects. We won't know how long it has been there unless we see an awful lot of lunar regolith on top of it, which means it's been there long times, like hundreds of millions of years, because the objects don't get destroyed on the moon very quickly at all. The estimate is that the artifacts we have on the moon now will last on the order of millions of years. And it'll be gradually destroyed by micrometeorites. That's a very long time. But the easiest thing to do to investigate something you see in a photograph is to bring the Lunar Reconnaissance Orbiter into a lower orbit temporarily and take much more detailed photographs of it. That's the fastest way to get new information. And of course, you can try to use the largest of the Earth's telescopes to get images in different frequencies and see if you can find out whether or not there's any thermal emission, would tell you whether there's an energy source. So there are various things you can do from a distance, passive observations, but ultimately you'd want to take a lunar lander and land nearby and go exploring.
Now, what about other planets in the solar system? I mean, would there be an advantage to, say, a Trojan asteroid at Jupiter, stationing something there?
I think it's a disadvantage because the Trojan asteroids of Jupiter are tens of times further away, and therefore hundreds of times more harder to resolve. That is, the size of the aperture you need to resolve a given feature on Earth goes as the distance away you are, how far away you are. So putting it very far away means you have to have a much bigger telescope or a much bigger sensor. And there really is no advantage to that when you can get very close on these objects that are nearby. So you could certainly try photographing something from a mile away, but you won't get very good photographs unless you've got a huge aperture, a big camera. It's just so much easier to get closer. So people who say, well, let's go look at Pluto, or let's look at the moons of look on the moons of Saturn, just don't seem to understand that the disadvantages are multiple. That is, not only are they far away, so the probe has to be much bigger, it's also much colder out there, and there's much less solar fluence to give you any solar power if that's what you want to use to power it. And a lot of things don't work in cold environments. At very, very deeply low temperatures, lubricants don't work well. Electronics function differently. It's a completely different environment. So why not get closer to the fire, closer to the sun? After all, that's where the interesting object is, the Earth. So I don't like the idea of hiding out in the outer solar system and making it hard for yourself. After all, you've come all the way from a distant star. Why hang back?
That obviously makes the moon an ideal candidate because you're right there, or as close as you can get. And if it came very long ago when Mars and Venus, possibly Venus, were interesting as well, they don't really have anywhere you could station anything except on the surface of the planet itself, which isn't going to be there now. What other ways can we search for artifacts on the moon? I noticed you mentioned in the paper, one, painting them with radar. Have we tried that yet? And has anybody looked to see if anything came back?
Well, certainly radar returns from the moon were gained as early as, I believe, like 1950. But that's just a bounce signal. Imaging of objects near Earth has been done for quite a few decades now by using the high-power radio telescope transmitters we have for space purposes, typically the Arecibo and radar and the Deep Space Network radars. And what we've done is produce images of objects nearby, such as asteroids that fly past. And we've imaged quite a few asteroids now. They have to be within the range of a few million miles in order to make that work because the return signal has to be strong enough. So we can certainly image the nearby co-orbitals. And the other thing you can do with radar, of course, is send a signal, ping them, see if you get a response. You'll get some kind of photons back, but I wonder if there's a live probe there, it might respond. If you actually sent a message, so to speak, or at least a signal.
If you sent a signal and it returned much stronger, wouldn't that be a good indicator that something's not quite right?
Well, yes, it would mean that there's somebody out there, and in fact, we should recall that in the early 20th century, when we first started producing radio signals, there were signals coming back from space, and we didn't understand them. It's now perhaps understood that these are some kind of a bounce from the magnetosphere that is delayed by processes in the magnetosphere of Earth, and not due to some probe sending a signal back, but that caused there was quite a lot of interest in those signals back in the 1920s. That's something people have forgotten about now. These so-called long-delayed echoes, they were called, of radio transmissions in the 20s. They're probably better explained as propagation phenomena in the Earth's magnetosphere, but it's really never been resolved.
Some of those were very long delays, though, that were reported back then. That almost seems to, how could the magnetosphere delay a signal for 7 or 8 seconds, And I'm not sure that's ever been addressed either. Now, do ham radio operators and people that work in that type of radio, do they still see these?
Yes, right. In fact, the most recent paper reporting on them and trying to figure out what they are was published in 1985, long after the original observations. So that's an argument that it's either a long-lived probe or it's a natural phenomenon that's a real echo. And so I think it's an unresolved question. And it's interested me that when I spoke to a number of astronomers, such as the Royal astronomer Martin Rees, a friend of mine, he had never heard of this phenomenon. After a long career in astronomy, he didn't know that these signals had ever been received.
Well, it's sort of an obscurity of radio itself. The only reason I ever found out about it was because of being a radio enthusiast, and I was like, "What could those be?" And then I found that people had connected it possibly as a technosignature. But then all work on it stopped. As you said, there hasn't really been any writing on it since the 1980s. And you'd think that would be something that people would look into these days. But there's a lot of that as far as technosignatures go, where somebody sees something awfully strange and then it just falls off the radar. Nobody looks again. Things like Cebulski's star, where you have these really strange transuranic elements, or at least what looked like indicators of those elements. And yet, as far as I know, no one's looked since to at least verify that that's what that was. So these things fall off the radar. Do you know of anything else like that that's sort of just fallen off the radar in astrobiology over the years?
Well, the obvious thing is the WOW signal, which only a few people have tried to look at in that direction and listen again, although just recently, just in the last month, a paper has been published where the Allen array was used to listen for quite a while, and they were able to say that it certainly wasn't repeating on timescales of like a week, because they'd listened to it for 100 hours at various times. And so now the people who are interested in the WOW signal, like Robert Gray, have decided it probably was some kind of leakage, a signal from a satellite which is not acknowledged. That is some classified satellite that we don't, because no known satellite was within view of that radio telescope when the WOW signal was received. So that's his opinion that he told me personally the other day. He thinks it probably was some sort of an unknown satellite.
Well, the weird thing about it, though, is by the time that was picked up, that frequency had already been set aside by international agreement. So nobody was supposed to be doing that. Now, of course, clandestine spy satellites don't always follow international agreements. But it seemed to me that if it was actually some sort of a spy satellite, you should have seen movement in the signal, and they didn't. It appeared to be fixed. So there's that. And I think they also, Dr. Ehman detailed in a write-up he did on the memorial website for the Big Ear telescope, that they were able to work out that it had to be at least half the distance to the moon to fit the antenna pattern, which really wouldn't fit a satellite in 1977. So I don't know that we are any closer to figuring that one out. I wish it would repeat, then we'd know.
Well, right, and that's what the few observations that have been done have been trying to see if it will repeat. So far, no good. It would take, I think if we get to having these omnidirectional observatories that are being proposed now for SETI, that would look at the whole sky all the time, that there's a chance you could see it repeat then, because you'd be observing all the time. the whole sky, not just one point in the sky.
Yeah, we're moving into that. As a matter of fact, I recently interviewed one of the scientists looking to do that pan-SETI, where you've got
Right.
much, much greater ability to search. Now, this brings up the other problem, though, is that if we do look for leakage, it doesn't repeat. But if we look for artifacts, that would be irrefutable. So if you find an alien artifact on the moon, how many of those, now you did a sort of a reimagining of the Drake equation and applying it to artifact SETI, how many objects could conceivably be on the moon?
Well, conceivably, within the time over which Earth has been an observable ecosystem, there have been about 500,000 stars come within 10 light years of Earth in that time. 500,000, that's a lot. If you want to ask how many have come within 100 light years of Earth, which is quite a ways to send the probe, of course, it's 50 million stars have come by. How many of those might have a civilization on it, of course, is complete unknown. But the numbers are big because stars come flying by.
So there could be thousands, maybe. I mean, obviously we don't know how many alien civilizations or how common alien civilizations are. But say that they're relatively common, then there should be a lot, right?
Mm-hmm.
And we should pick it up fairly quickly.
There could well be a lot, yes. And some of them would be very old, some of them not so old. And therefore it's really worthwhile to explore the surface of the moon because it's a potential museum of extraterrestrial objects. And in fact, the surface of the moon, because it's been there so long and we've circled around the galaxy so many times that it is actually has if you dig down through the regolith, you get a sample of what the environment, what fell onto the moon over geological time scales. So you can do a kind of a galactic geology by boring down into at depths, say tens of meters onto the moon. And there are proposals that we ought to do that in the near term with lunar expeditions, is take core samples all the way down as far as we can. And I think that's another reason to go to the moon that's seldom mentioned.
Now, my last question for you today is, all right, so say we find an object and we get a rough date on when it was deposited. How hard is it to extrapolate back these star systems that are passing by to try to figure out where it came from? Say it's something that could be, I don't know, 1 million years old. Actually, let's go much younger. Say 50,000 years old. Could we trace that back to a star system, or is it just a billiards game effect where eventually you just can't tell where it would have originated from?
Well, we can actually. The good news is that the Gaia probe has given us a good mapping of the locations and velocity vectors of many stars near us. In fact, there's about 700 observed stars that have come within some reasonable distance of Earth. And we know when they came by, there's quite a few. If you pick 50,000 years, you'll get a number like 10-ish stars have come reasonably nearby, 50,000 years. One note about that is that Alpha Centauri is now 4.25 light years away, but 20,000 years from now, it'll be 3 light years away. And other stars like Ross 248 and Barnard star are going to come closer than Alpha Centauri is now. So we can run that movie backwards and find out what came by. If we found a probe and we said it came 100,000 years ago, we could find a small group of stars that were reasonably close at that time from the database we already have.
Now, what of the future? Is there anything coming our way that we've been able to work out that might be useful for us to drop a probe there? Is there anything of interest coming our way?
There is a star, I don't have its name at hand, that's going to come very close to us in about 1 million years. Very close, meaning like 1,000 AU, something like that. And of course, as I mentioned earlier, there's Solstice star that came within 0.8 of a light year 70,000 years ago, and we now know where it is. If it had sent a probe, well, I think we ought to, although it's now much further away, we should be listening to see if it's sending any messages to us, knowing 70,000 years ago that there were these primates that maybe had some possibilities to develop, that then they might be sending some messages once in a while to see if we would respond.
It's interesting to kind of wonder, even without a probe, if you have these star systems passing by, presumably some of them are going to have material around them. Could the Oort cloud be collecting materials from stars passing by? So could we go out and look at interstellar objects that far out that we've captured?
Yes, and they would get some objects from us too. Anything that comes within the Oort cloud is going to exchange material in some way by gravitational interaction. Of course, the major interaction that we could be concerned about is that they would disturb something in the Oort cloud that would then plunge into the inner solar system and hit us, as comets do. And the Solstice star, for example, at 0.8 of a light year, is going to produce a rain of comets about 3 million years from now when they finally reach the inner solar system.
Hopefully by that time we will be able to deflect them. All right, Dr. Benford, I thank you again for appearing with us, and I hope you'll come back next time you release some more papers.
Be happy to do so.
Thanks for listening. I am futurist and science fiction
Jonh,
author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author Jonh Michael Godier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?